Usually when we talk about a physical warehouse, the security is, well, it's pretty straightforward. You build a tall chain link fence, you slap some heavy padlocks on the doors, and maybe you hire a security guard with a flashlight.
Right, because the perimeter is visible. It's entirely tangible. You know exactly where the threats are supposed to come from, and you can just point a finger directly at where your most valuable assets are sitting.
Exactly. But then you step into the world of enterprise data storage, and suddenly that chain link fence is completely useless.
Yeah.
I mean, we're looking at a landscape where the threats are invisible, the space is entirely virtual, and the warehouse needs to stay open 24/7.
Even if a Category 5 hurricane completely flattens the physical data center.
Yeah, exactly. So, welcome to the deep dive. Today we have a highly focused, very specialized mission for you. We're dedicating this entire session to reverse engineering the hardest concepts, the questions, and the answers from the NetApp NS0-165 exam.
Yes. The NetApp Certified Data Administrator on ONTAP exam. It really is the gold standard for proving you know how to build, optimize, and protect that invisible fortress we were just talking about.
And whether you are actively cramming for the NS0-165 right now, looking to upgrade your IT credentials, or you're just intensely curious about how massive global enterprises keep their data secure, shrunk, and always online, this session is your ultimate cheat sheet.
Absolutely. And just to set the stage for you, when you sit down for this exam, you have exactly 90 minutes to tackle 60 items.
Right, and the formats vary a lot. You've got multiple choice, multiple selection, matching, drag and drop. And you need a 64% to pass, delivered in either English or Japanese.
But we aren't going to just drill you with a dry, sterile list of 10 questions from 1 to 10. That's not how we do things here.
No, not at all. We are going to group these practice questions into a logical journey, starting with locking down the data, so security, then moving to organizing the space, which is efficiency, and finishing up with keeping the system actually running.
Architecture and availability, building from the ground up. Because, honestly, before an enterprise can worry about how efficient or fast their storage is, they have to ensure that data is safe.
Safe from outside attackers, obviously, but also safe from inside mistakes. So, okay, let's unpack this by diving straight into those internal threats.
Let's do it. Question 1 territory.
Right. So the question asks which feature requires a secondary administrator to approve sensitive storage operations. Now, a lot of administrators assume that if they set up role-based access control RBAC, their system is secure from internal sabotage.
Oh, yeah, that's a huge misconception. But if an employee already has full administrative rights, RBAC isn't going to stop them from going rogue.
Right, because RBAC just dictates what permissions a user account has. If you have the keys to the kingdom, RBAC just confirms that you're allowed to open the doors. It doesn't question your intent once you're inside.
Exactly. It just says, yep, you're the admin. Do whatever you want.
Well, then some might argue that security multi-factor authentication MFA solves this.
Yeah.
You force the admin to use a fingerprint or an authenticator app.
Sure, an MFA is critical for verifying identity at the front door. It proves you are who you say you are when you log in. But think about the timeline here.
Yeah.
Once you pass the MFA check and you're authenticated into the ONTAP command line, MFA basically goes to sleep.
Oh, right, because you were already in.
Yeah, it does absolutely nothing to stop you from accidentally or maliciously deleting a massive mission-critical database 30 minutes into your session.
Which brings us to the actual answer. This is where NetApp introduces multi-admin verification, or MAV. And I love this concept because it perfectly mirrors that classic movie trope,
Just submarine one.
Yes.
Yeah.
You're on a nuclear submarine, and they receive the order to launch the missiles. One captain can't just press a button on their own console. You need 2 captains standing on opposite sides of the room, turning their launch keys simultaneously.
And that dual control mechanism is exactly how MAV operates. It specifically guards against insider threats and catastrophic accidental deletions. By enforcing a secondary administrator's approval for sensitive actions like deleting snapshot copies or altering core security configs, you ensure no single person has the unilateral power to destroy the environment.
The operation just hangs there in a pending state until that second admin says, yeah, this is okay.
Exactly. So our internal admins are kept in check.
But the external threats are constantly evolving, particularly ransomware. Which brings us to question 2. If I'm an IT director and I deploy ONTAP's Autonomous Ransomware Protection ARP, my instinct is that I want this system to be hyper-aggressive from second.
Right. You want it to just lock everything down.
Yeah. Like if it's under attack, shouldn't it just automatically block all unknown write requests or immediately encrypt all my existing volumes for safety? Why is the answer learning the typical data behavior?
Well, let's follow that aggressive logic to its conclusion. If the system automatically blocked all write requests the moment you enabled the feature, you would bring your entire company's business to a grinding halt.
Oh. Yeah, I guess no one could save a spreadsheet.
Right. No database could update a transaction. It would essentially be a self-inflicted denial of service attack. And as for encrypting existing volumes on the fly as a defense mechanism, that would be massively disruptive to your CPU overhead and your storage latency.
Okay, fair point. What about deleting suspicious snapshot copies? That's another reaction some might think is smart.
But snapshots are the safety net. They are the ultimate recovery tool. Deleting your own snapshots is exactly what the ransomware attacker is trying to do to prevent you from restoring your data. So ONTAP doesn't do any of those things.
Which is why the very first primary activity of autonomous ransomware protection is simply learning.
It has to go to school first. It must establish a baseline. You cannot spot an anomaly if you don't mathematically understand what normal looks like for your specific environment.
So during that initial phase, it just sits quietly.
Yep, it sits in the background analyzing baseline file access patterns. It's looking at read and write frequencies, typical file extensions, and only after that baseline is firmly established can its machine learning detect the rapid encryption or unusual write spikes that signal a live attack.
Okay, so we've got dual keys for our admins and an AI learning our file behaviors to detect external attacks. Let's move to question 3. What about the data just sitting quietly on the physical disks? The exam heavily tests NetApp aggregate encryption, or NAE.
Oh, this is a big one, because there's a historic conflict here. For years, encryption has been the mortal enemy of storage efficiency, specifically data deduplication.
Right, it's a fundamental clash of technologies because deduplication saves space by scouring your storage for identical blocks of data, keeping only one copy and replacing the rest with tiny pointers.
But encryption scrambles everything into unreadable ciphertext. So 1,000 identical Word documents will look like 1,000 completely unique, randomized blocks of data once they're encrypted. Nothing looks identical anymore.
Which means if you encrypt at the individual volume level, deduplication across different volumes becomes mathematically impossible. Your space savings just plummet.
Yeah, and some legacy systems simply accept that deduplication has to be disabled entirely, or they restrict it to working only within a single isolated volume.
But NetApp aggregate encryption solves this. And this is vital for anyone taking the exam to understand. NAE allows deduplication to work across all volumes within the aggregate.
To understand why that works, we really need to define the architecture. In ONTAP app, an aggregate is the broad physical domain, the actual collection of physical hard drives or SSDs. Volumes are just the logical containers carved out of that aggregate.
So by applying the encryption at the aggregate level rather than the volume level, multiple volumes are forced to share the exact same encryption key domain. So what does this all mean for the data?
It means the encryption happens underneath the deduplication engine. Because the volumes share the same key, identical data blocks written to different volumes will still result in identical ciphertext. Oh, wow. So the dedupe engine can still see them as matching.
Exactly. It can easily identify those matching encrypted blocks, strip out the duplicates, and save you terabytes of space. You get military-grade security without sacrificing a single byte of storage efficiency.
That is brilliant. And it's the perfect transition into our second segment, the smart warehouse. Because now that our data is guarded, we have to talk about economics.
Storing petabytes of data on high-performance solid-state drives is incredibly expensive. We need to optimize every inch of space.
And a lot of the exam focuses on what happens to our storage efficiencies when we start moving things around the warehouse. Let's look at question 4. What happens to data deduplication savings when moving a volume between aggregates on the same node?
Moving data is a major pain point. You have to rebalance loads, retire old hardware, or upgrade to faster nodes.
So a common fear, or at least a very tempting distractor option on the exam, is that the deduplication savings will be completely lost during the move, or that the dedupe process will just permanently stop working on that volume. And those fears are totally based on older, less sophisticated storage arrays. In legacy systems, when you move a highly deduplicated volume, the data
Rehydrates, meaning as it moves across the wire, all those tiny pointers are expanded back into their original full-size blocks.
Right. If you had a 100 gigabyte volume that was deduplicated down to 20 gigabytes, it blows back up to 100 gigabytes on the destination array.
It's like moving houses. Usually you have to unpack all your perfectly vacuum-sealed bags of clothing, throw everything in the loose cardboard boxes, put it in the moving truck, and suddenly it takes up 5 times as much space.
That's a great analogy, but ONTAP fundamentally changes that mechanism. When a volume is moved between aggregates on the same node, the space savings are entirely preserved during the move.
They don't unpack the bags.
Exactly. The system transfers the data blocks alongside their deduplication fingerprints and metadata. It literally copies the vacuum-sealed bags as they are. The destination aggregate simply registers the existing pointers.
Ensuring administrators don't suddenly run out of physical capacity just because they needed to shift workloads around. That prevents so many 2 a.m. storage capacity alerts.
Absolutely.
Now, speaking of optimizing space, question 5 leans heavily into Fabric Pool, which is NetApp's cloud tiering technology. You're combining local, high-performance solid-state drives with cheap, deep cloud storage, like AWS S3 or Azure Blob.
But you have to set a tiering policy. The exam asks, which policy moves only inactive data blocks to the cloud tier?
Right, you have a few options to evaluate. Let's look at the distractors. If you choose the all policy week...
Oh, well, the system acts like a dump truck and moves every single block of user data to the cloud.
Which immediately bottlenecks your active mission-critical databases because suddenly every read and write operation has to travel back and forth across the internet. It defeats the entire purpose of buying fast local storage.
Then you have the none policy, which just turns tiering off. Everything stays on the expensive SSDs, burning through your IT budget.
Right. And the snapshot-only policy is exactly what it sounds like. It ignores your cold user data and only relocates your backup snapshot blocks to the cloud.
So to move just the inactive user data, you have to configure the auto policy. Think of it like a highly advanced automated data lifecycle manager.
I compare the auto policy to a smart closet. You know, it monitors what you wear. Yeah. In any given volume, maybe only 20% of the data is hot, actively being read or written to by your applications right now.
And the other 80% are old PDF reports, completed project files, or archived emails from 3 years ago. They're cold.
Right. So this smart closet automatically ships your bulky winter coats to a cheap storage unit in July, but keeps your daily sneakers right by the door.
Exactly. The auto policy monitors the temperature of those individual blocks. It uses a cooling period, which is totally customizable, say 31 days. If a block hasn't been accessed in 31 days, the auto policy seamlessly detaches that block from the local SSD, wraps it up, and relocates it to the cheaper cloud object storage.
But to the end user or the application, the file still appears to be sitting right there on the local drive.
Yeah, it's completely transparent cost optimization.
Okay, but let's jump to question 6. What happens when you aren't paying attention, you're not tiering enough to the cloud, and your local FlexFull volume simply runs out of space? It's about to hit 100% capacity.
Panic mode for a lot of admins.
Truly.
Yeah.
Now, honestly, looking at the options, the easiest fix would be for the system to just automatically delete the oldest unaccessed files to make room for the new incoming data.
Oh, wow. No, that is the ultimate taboo in enterprise IT. A storage administrator would rather the entire system crash than have an operating system arbitrarily delete user data without explicit permission.
Okay, message received. Deleting data is a sin. What about shrinking other volumes? The system sees that the HR volume has plenty of free space, so it forcibly shrinks HR to give space to the accounting volume.
That's robbing Peter to pay Paul. It violates the logical boundaries you've set up and can cause severe compliance and operational issues for the volume being shrunk.
Right. And obviously, shutting down the entire storage virtual machine just because one volume got full would take multiple departments offline. Unacceptable overreaction.
Completely. This brings us to the actual default mechanism ONTP uses, the auto-grow feature. Yeah. When that FlexVault is almost full, it dynamically increases the volume size using available space from the underlying aggregate.
It's just so elegant. The FlexVault is just a logical container. When it detects it is hitting its capacity threshold, it quietly queries the physical aggregate below it. If there is free, unallocated physical space down there, the volume just expands its own boundaries.
The application keeps writing data, the users never see an error message, and the service remains perfectly available.
It fixes the problem before a human even knows there is a problem. All right, we have our fortress locked down securely, and our warehouse is brilliantly organizing its own space. But that leads us to segment 3, the highway system.
Architecture, access, and uptime.
Because a secure, perfectly organized warehouse is completely useless if the roads leading to it are blocked, or if the delivery trucks are dropping sensitive cargo off at the wrong loading docks. We need to look at networking.
This is the crucial bridge between how the data is stored internally and how the clients out in the real world actually connect to it.
Let's take question 7. The exam expects you to know exactly which component isolates network traffic and management for different departments operating on a single ONTAP cluster.
Multi-tenancy.
Right. Now, a networking engineer might assume the answer is simply creating different broadcast domains or utilizing separate physical network ports.
Yeah, because a network engineer thinks in terms of layer 2 routing. Broadcast domains and VLANs will isolate the network packet, sure, but they do absolutely nothing to isolate the storage management, the root volumes, or the administrative access.
And relying on physical network ports is just inefficient hardware segregation. You can easily have multiple departments securely sharing the exact same physical Ethernet port. So what about the cluster interconnect?
Oh no. The cluster interconnect is the strictly private, highly redundant back-end network that the NetApp nodes use to talk to each other. Client data and departmental traffic are never allowed to touch it.
So the true solution for multi-tenancy is the storage virtual machine, or SVM. You'll often see them referred to historically as vServers.
SVMs provide complete logical isolation at the storage layer. Each SVM acts as its own independent storage array. It has its own dedicated network interfaces, its own unique security policies, its own administrator accounts, and its own dedicated volumes.
I always visualize an SVM like a luxury apartment building.
Yeah.
Everyone in the building shares the exact same concrete foundation, the same physical walls, and the same power grid, which is the physical ONTAP cluster.
Right.
But every single tenant have their own locked front door, their own private plumbing, and their own completely secure living space. The accounting department's SVM has absolutely no idea that the human resources SDM even exists on the network, even though their data might literally be spinning on the exact same physical hard drives.
It is the foundation of secure cloud architecture. Now, once you have those isolated SVMs, how do the host servers actually mount the storage? That's question 8.
Right. Which protocol provides block-level storage access over an existing Ethernet infrastructure without requiring dedicated host bus adapters? Let's filter these out. Network File System NFS is incredibly popular, but it provides file-level access, not block-level. So that's out there.
Block-level access means the server treats the storage array exactly like a local internal hard drive, issuing raw SCSI commands. Traditionally, to get block-level access, you used fiber channel.
But the requirement states without requiring dedicated host bus adapters. Fiber channel requires incredibly expensive, highly specialized physical host bus adapters, or HBAs, in the servers, plus specialized fiber channel switches. The same goes for NVMe over fiber channel. Still relies on that expensive physical fabric.
Which leaves ISCSI as the hero here. ISCSI takes those raw block-level SCSI commands and encapsulates them inside standard IP packets. It then transports them over the exact same standard commodity Ethernet networks you already have deployed in your data center.
It's an incredibly cost-effective way to build a robust storage area network. But jumping to question 9, relying on standard Ethernet networks to transport crucial block storage introduces a massive risk.
It does.
What happens if an Ethernet cable gets unplugged or a network switch simply dies? If that connection breaks, the database crashes.
And that is the inherent risk of a SAN environment. You never want a single point of failure between your host server and the storage array. So the architectural standard is to cable the server to the storage using multiple redundant physical paths crossing different switches.
But the host operating system needs to understand what is happening.
Yeah.
If you just plug a Windows or Linux server into a storage array with 4 cables, the OS might just see the exact same hard drive 4 separate times and completely corrupt the file system trying to write to all of them.
Exactly. And you can't rely on generic network load balancing. That's designed for balancing web traffic across servers, not handling block I/O. And dynamic routing protocols are strictly for network routers finding IP paths. They don't manage storage connections.
And the storage array can't fix it from the back end using automatic volume migration. I mean, if the cable is cut, the volume can migrate all at once. The host still can't reach it.
The solution must live on the host side. You must configure multipathing software like DM multipath on Linux.
Right. Multipathing software sits on the host server and intercepts the storage connections. It recognizes that those 4 physical cables all lead to the exact same logical unit of data. It consolidates them into a single virtual drive for the application.
And if a storage controller fails or a switch just bursts into flames, the multipathing software instantly detects the dead path and automatically redirects the block I/O traffic down an alternate surviving path.
The database running on the server never even knows there was a hardware failure. It just experiences a microscopic pause and keeps running.
It's practically magic.
It really is. Okay, that handles a switch failure perfectly. But let's take it one step further to the absolute extreme worst-case scenario for question 10.
The cratering event.
Yes. The entire primary data center loses power. We aren't just losing a cable. We're losing the entire building. The exam demands a data protection solution that provides synchronous replication for zero data loss recovery in an active configuration.
Let's focus on the metric the exam is demanding. Zero data loss. In disaster recovery terminology, we call that a recovery point objective, or RPO, of 0.
So if we look at the distractors, local snapshot copies offer zero disaster recovery. I mean, if the primary building burns down, your local snapshots burn with the physical drives.
Exactly. Then there's SnapVault, which is fantastic for deep archiving, but it's an asynchronous backup tool. It might update once a day. If disaster strikes at 4 p.m., you've lost an entire day of business data.
Standard SnapMirror is the backbone of most NetApp disaster recovery plans, but it is also asynchronous. You can schedule it to replicate every 5 minutes, which provides a near-zero RPO, but near-zero is not strictly zero.
No, it's not. Data written in that 5-minute window is gone forever.
Which means the only architectural solution for zero data loss is SnapMirror Business Continuity, or SMBC.
Because SMBC utilizes synchronous replication. When a host server writes a block of data to site A, the local storage array does not acknowledge the write back to the application until that data has also been successfully transmitted across the network and committed to disk at site B.
Both sites are guaranteed to be perfectly identical at the exact same millisecond.
Furthermore, it provides an active configuration. Both data centers can serve read and write traffic simultaneously. If Site A vanishes off the map entirely, the system transparently redirects the application hosts to Site B. They take over instantly with uninterrupted availability.
It is the pinnacle of enterprise resilience. Thank you all for joining us on this deep dive. Good luck on the exam, and remember to always keep questioning how your data is actually stored.